Hello, everybody, and welcome to the Week 9 lecture for QSO-600 Operations Management. This week, I'm going to basically go over a basic material and labor resources plan. This is something that you could use. It's very basic, mind you, but something you could use to understand the amount of materials and labors that your processes will be using. This is aimed more towards manufacturing processes, but you could use something similar for service-based processes. You just, instead of using materials, you would use steps or service products that add value. So if you have any questions over that, please let me know, and I can see if I can put something together for services. So I'm also going to cover statistical process control briefly. I gave a little bit of a discussion on this earlier in the class during week 2 or week 3, but I'm going to go into more detail now, going over special cause variation, common cause variation, and how to understand what the voice of the customer, what the voice of the process is telling us. And I'm going to basically go over queuing theory. This is mainly for services, but for instance, IT uses this to understand throughput of people or signals going through a network. So queuing theory basically in general deals with how a product or service flows through a particular process. I'm going to go over something called Kingman's equation, which is a good way of understanding the queue time and how to best improve the flow of materials through a process. So when we create a material and labor resources plan, these two, you can go for the product decomposition and the production workflow. So when you have your product decomposition, if you remember correctly, the top level we had 1100, 1200, 1300, 1400, the peripherals. So for you, as a quick refresher, the first digit is the first level, or tier 1. The second digit is the second level. Third digit is the third level. And if you had a fourth digit, which we do here, then whatever's on the fourth digit would go underneath here. Like for instance, if the uppercase had 4 items, we would list the uppercase items underneath the uppercase, and they'd be like 1111, 1112, 1113, 1114. Now, when we do this, basically, we will decompose our components down to the lowest level, down to the screw or the nut or the gasket or whatever, okay? Usually it goes down to the consumable levels. The consumables are the lowest level, and then the next level higher is the first level repairable or the first level main part. So you've got different levels of assembly. And in a larger production system, as I mentioned before, each of these numbers would be the number for the assembly instructions. So 1120 would be the assembly instructions for the lowercase. And like, for instance, if we had different revisions over time or different models or things change, you'd have 1120-1 for like the -1 type, or -2 or -3. So over time, we can create this set of processes that denotes how we will, what goes into the product and also what is required to build it as far as labor. So if you remember, we had our workflow, and this basically is how we can determine how the product, how the parts and labor is used to assemble this product. So for instance, what you could easily do is, like, let's say for 1210, you can make a swimboard diagram where you would have it where each lane is a particular person who touches the product, and then you would have like 2 or 3 hours, whatever it is, and as it swims through the swim lane, you can move the product back and forth between labor. Then at the end, you could add up all the different hours that shows how much is used for each swim lane or each type of labor. So then all of those can be placed into a either a work breakdown structure if you're doing project management, or a manpower allocation structure, something that is used for identifying manpower needs across a certain process or a certain thing. So you can do this. So in this regard, then you could also, like, let's say that we had just built this final assembly and test procedure. What you could do is you could flow out all of the different people in a swim lane. Then you can connect the swim lanes together to see how the manpower can be allocated between processes. Then as you do this, you may move, let's say the BIOS and the operating system together, because they both may use different resources. So then you may move things around so that you can maximize the manpower, as long as the materials can flow through it. Like for instance, you wouldn't be able to do a burn-in test before the operating system is put together, obviously. So you'd have to put them in order, but you can also allocate the steps based upon the availability of the individuals and the parts as they flow through. So using this system, you can decompose each level to the lowest level, to the consumable level, like the screw, bolt, fastener, gasket, whatever. And then for each of the assemblies, you would create assembly instructions for each sub-assembly up to the main assembly. So if you looked up kid-friendly computer, you would have your assembly instruction for that would be like first, perform 1100 case assembly instructions, perform 1200 hardware instructions, perform 1300 software instructions, 1400 it would be peripherals instructions. And if you had it electronic, you would click on this and it would show you, okay, for 1400 peripherals, you must do 1410, 1420, 1430, 1440. Then and let's say if each of these had another level, you would click on that and you would do it. So you could create this very decomposed and very structured material and labor resources plan for any product. And some of these can be very complex. I've seen them, I've used these in engineering when we design systems. And they can be very complex, obviously. Or they can be very simple. It just depends on how far you need to go. But normally I go down to the consumable level. Once we start to hit the consumable level, then we flow basically where the assembly starts from there, what makes the most sense. Usually, as soon as the consumables stop, then I start the assembly, the labor resources at the first level of assembly. So here is a simple material and labor resources plan. I just put this together really quickly to show you what one would look like. And basically, I have 3 levels: level 1, level 2, level 3. Level 1 corresponds to the top level, 1100, which would be, well, in this case, actually be level 2. But 1100, 1200, 1300, 1400 is level 1. I guess in theory, the 1000 will be level 1, but you can make this level 0, whatever. So level 1 would be the top level assembly. Okay, so here I've got two units that I've broken out, the case and the hardware. In reality, you'd have one for 1100, 1200, 1300, 1400, all of your different assemblies. And then for each of those, you make a level 2. Okay. Now I like to break these out into different levels, like level 1, level 2, level 3, level 4, because then it makes it easy to sort. So like you can make this in Excel so that you would only show auto sort level 1, all the level 1 items. So this helps you to organize things, make sure that you didn't miss anything. So you say, okay, I just want the level 1. And then you may say, I want the level 1 and level 2, and you can compare this to your decomposition that you made earlier to make sure that everything is included here on your chart. Okay, and then level 3, basically I have as consumables or bottom level assemblies that don't require labor. So from here, level 1, level 2, these would require assembly. And as you notice, I added a quick labor tally. I basically gave it 3 tasks: assembly, testing, and handling. And these are in hours, 322 and 103. And basically, I add up all of these to equal here. So for instance, for the case, I would need 4 hours of the assembly manpower. I would need 2 levels of testing, and I need 5 hours of handling. And of course, if you had different ones, you basically add them up as you go along. So same here. So for instance, we have 5, 7, 6. So 5, 3 plus 2, 7, 2 plus 5, and 6 is 5 plus 1. You can make a third level where you may have the motherboard. Like for instance, you can have the motherboard where it may add up to the third level. Let's say if level 3 had maintenance, you could put down hours here, then you have them all add up to the motherboard, and then you can have it so that these automatically add up just the green sections, just the level 2. And this will only add up to level 3. So you can automate a spreadsheet to make this very easily. So as you change your operations plan, let's say you miss a step, or you find out through your dry runs that you use more hours for certain things. You change the hours, all of a sudden, all of your hours will automatically change. So you can use Excel to do this for a very basic one. Obviously, if you're designing a car, Excel may not be complex enough. But if you're designing part of a car, let's say you're designing a new steering wheel, you can make it in Excel and maybe import it into a database of some sort. So this is a very simple material and labor resource plan. So you have your materials, which is your items here. Okay, and you could put like a number, like each, like how many, like 3 cases, or maybe you need two sets of hardware, or 4 memory, or whatever. So you can place another category here, basically says how many, and then once you do that, like for instance, let's say we need 5 plastic shells for the lower case, then you could also make another category here that'll count how many 1221 memory cards you may need for each assembly. And then when this is all put into a database, it makes it easy to look up. So you would pull this information. If you're building a car and say, okay, or if you're building a computer and you want to put a memory card into it, you'd say, okay, well, I want to, how many 1221s do I need to order? And in theory, all of this is pushed into a material requirements plan, where we say, okay, for each, we're going to build 50 of these, and for 50 of these, we need 50 times everything on this. So you would send this order off. You may have some deviation in case you have issues with like broken parts or parts that may not conform. So you may change it, maybe you buy 52 units worth of stuff. Ideally, in a perfect world, you would order 50, but sometimes, you may order 51, 52, or you may just have safety stock. So you may order 50 and then pull from the safety stock like a pre-ex. A pre-extended bin is a set of bins or locations where when it gets down to a certain level, you reorder. So you may have all these in a pre-ex situation where if you get down to 7 screws, oh, I just noticed I didn't put down 1113 here. So sorry about that. So if you need 4 screws, you may say, okay, I've got a container of 200 screws. And when we get down to a certain pre-order level, which you could use what's called economic order quantity, or other ways to calculate the safety stock levels, you would say, okay, once we hit 20 screws, we order a new batch of 50 or 100 or whatever is decided. So all of this can be used for both understanding what goes into a component, what needs to be ordered, and how much labor is required for assembly. And at the top level, like for instance, let's say if we had a level 0, you add up all the yellow ones, and then it tells you, oh, okay, like in this case, if this was the whole computer, which it isn't, if this was the whole computer, we'd say, wow, we need 9 hours for assembly, 9 hours for testing, 11 hours for handling. So you could roll it up to the top level for like if you're doing bids for new business, or if you're designing something and you want to understand how a similar product works, you can use this for a prediction of a similar design. Now, statistical process control. This is something that is, in my opinion, is extremely important to anyone who works in operations, because a very good understanding of statistical process control will save you a lot of time and money. In many cases, statistical process control will help you tell you what to do and what not to do as far as improving a process is concerned. So many times I've seen where, and I'm going to cover this in a minute, where they would address all common cause variation and special cause variation, and as a result make the problem worse. Then as the problem spirals out of control because they're doing the wrong corrective actions, they get frustrated because they don't understand what the process is telling you. So Statistical process control in general is a method for using statistics to measure the health of a process. And basically what this tells us how things are going through a process and how things are coming out at the other end. And there's two types of measurements that we use. I talked about these briefly in week 2, I believe. It was the one where we talked about the house of quality. You've got the voice of the customer. And the voice of the customer basically is whatever the specification state. In a perfect world, you would design a product with specifications that best meets what the customer is expecting. So that would be the voice of the customer. It's sometimes called the voice of the engineer because the engineer is one that translates customer requirements into specifications. So voice of the customer measures conformance to specifications. And we compare the process outputs to the specifications to determine how the process is performing relative to the specifications that we've set. So this is the one that's used the most of the time. Now, the other one that we have is called the voice of the process. And this one is very important because this is completely different than the voice of the customer. This measures the statistical variation within the process. And we compare this, and instead of comparing it to specifications, we compare the process outputs to control limits. The control limits are a statistical measure of how much variation is within the process. Usually we use 3 standard deviations. This is very important because when we deal with special cause variation and common cause variation, these two concepts are critical in understanding what to do to fix your problem. Now, the main types of charts used in statistical process control, control chart and a histogram. There are many different other types. There's box plots, scatter plots, regression plots, ANOVAs, cause and effect diagrams. But as far as measuring the performance of a process, these are the 2 main ones that we use. So the control chart basically shows how a process, not so much changes, but how a process performs over time. Okay, and you've probably seen these. What you do is you would run a process over a certain period of time, you gather the measurements of how it performed, and you put it across a line. I'm going to show you one in a minute. So, and a histogram represents a distribution of a population measured over a certain interval. So, like, let's say we have a process where we're drilling holes between 2 and 4 inches. So we would measure a whole bunch, and we would stack them up in a bar graph to show how many times we hit each of the different intervals that we select for our data points. So I'm going to show that also in a minute. So the types of variation in statistical process control, this is very important. I just mentioned these a minute ago, but I'm going to go over them again. Special cause variation is any variation that lies outside of the upper control limit or the lower control limit. The upper control limit and lower control limit is the statistical point of control in which we can safely predict that future performance will lie. Okay, and this is the plus or minus 3 standard deviations. So if we get special cause variation, basically something has fallen outside of the upper control limit or the lower control limit. In that case, it requires improvement of the particular data point. That basically that one data point has something that is operating outside of the system norms. So you look to that to see if you can correct it. Common cause variation is one that is more familiar to everybody. And common cause variation is any variation that lies outside the specifications but within the upper control limits and lower control limits. So basically, any common cause variation, basically any points that are outside of the specification limits. I'm going to show you a picture of that in a minute, but it's still within the system control limits. When this occurs, if you focus on that individual data point, you are wasting your time in general. You may get some benefit, but basically any data point that falls between the upper control limit and lower control limit is working within the system boundaries. So in order to fix anything that falls within the system boundaries, the upper control limit and lower control limits, you must improve the system, not that individual data point. This is extremely important. So if you have if you're measuring the performance of, let's say, a call center, and one person is always calling, taking calls outside of the specification limits. If the person is still performing within the system's limits, you'll get much better benefit by focusing on the system, improving the system as a whole, because that probably means that your system is out of control. I'm going to tell you that. I'm going to go over that in a minute. So this is a control chart. As you see here, you have the upper control limit and the lower control limits are in blue. Okay, as you can tell here, the upper control limit is 6.14 and the lower control limit is 2.13. They fall outside of the tolerance level, which is 4 plus minus 1. So the specification limits is 3 to 5, because 4 plus 1 is 5, 4 minus 1 is 3. So as you can see here, all of these points fit inside the specification limits, but they are out of statistical control because the upper and lower control limits are outside the boundaries of your specification limits. So what this basically means is this performance is unpredictable within the specification limits. So and this happens a lot. So all this is going to tell you is how the process performs within your upper control limits, your lower control limit, and your specification limits. So if you just focused on the performance within specifications, you think, oh, everything's fine, everything's great. But this graph is telling me that the system is out of statistical control. You cannot safely predict that all of these will be maintained within the specification limits, not without extra help. Now, if you remember earlier, I talked about special cause variation and common cause variation. This is another graph here that I had from week 2. And if you can notice, the common cause variation is all the variation that's within the control limits. Okay, everything that's within the control limits. So if a data point falls within this area, it's basically performing as the system performs. Okay, if it falls outside of the lower and upper control limits, we now have special cause variation. Now, something outside of the system is causing this variation. So like, for instance, this data point here is a special cause. So we can look at that to determine how to improve that performance. But if you go here, which also lies outside of our specification limits, if you try to improve this particular performance here, you won't have much luck doing so, because this actually falls within the control limits. So it's working within the limitations of the system. So for this point, you would improve the system. You would make the whole process tighter so that the upper control limit and lower control limit band would be shorter. Ideally, the upper and lower control limits would be inside your specification limits. That would be the best way. Then you are in statistical control. Now you can safely predict that your process will perform inside that limit, that area. Okay. Now, if you remember the data that I had earlier, okay, you notice that all of these dots are inside of our specification limits. But they're also the upper and lower control limits are outside the bounds of the specification limits, basically being out of statistical control. Now, if we take a histogram of that data, oops, sorry, I'm going the wrong way. If we take a histogram of that data, this is what we see. In a healthy system, our data would form a normal distribution. It would be like a normal distribution. But if you notice here, all of our data mainly sits on the left and right side. Okay, so this tells me that there's something in the system that's causing this. And what it could be is that these parts are showing up to the assembly outside of statistical control, outside of the specification limits, but they're being worked so that they just barely fit inside the specification limits. This is when you have, people intentionally having to fix, this is when you have rework demand, which I'm going to talk about types of demand in the system in a minute. So you have people reworking the materials so that they fit inside this band here. In a healthy process, you'd have a parabolic normal distribution. Okay, so this is very important. So a histogram is very good at showing us how everything falls. And here you can kind of see where there's a little bit of where like everything is sitting on the left and right edges of the specification limits. So this is very important to understand. So I usually like to use both a control chart and a histogram to show me this kind of information. Okay. Now, queuing theory. This is mainly, I'm providing this mainly for services, but it can be used for manufacturing. And as I said earlier, IT uses this to determine the throughput of signals through a network. So the queuing theory basically is defined as a study of waiting lines. If you go to the DMV, it's a study of people queuing to wait to get their driver's license, or if people are sitting in line waiting at Disney World, waiting to go on a ride. It's the study of these lines. And as it says here, it's applicable in both service and manufacturing operations. The difference is in manufacturing, we use it contains work in progress. So there's parts that are in these queues, okay? In services, the queues contain customers. So services are more vulnerable to queues than manufacturing because work in progress doesn't complain and quit shopping at your place, whereas customers do. So each queuing system, we have 4 different types of queues that we look at. We have arriving customers or arriving parts. They're the ones that arrive at the front end of a process. We have the waiting customers, the ones that are waiting at the front of the process, waiting to be processed, okay? We have in-service customers. These are the ones that are inside the process awaiting output out of the system. And then we have departing customers, people who are leaving the process. So they were in service at one time, but now they're departing. They've been done. They're going to go off to another process. So these are the 4 types of queues that we deal with. And we study this because queuing theory allows us to predict your ability to meet future demand on a process. We're able to use what is called Kingman's theory. There's another one called Little's law. Kingman's theory is a little more complex, but Little's law, you may hear that sometimes in queuing theory. So just in case you want to know. So we like to use queuing theory because we can understand how much stuff is going to stack in a process, both in the system, outside the system. Now, when we deal with the process, there's 3 types of demand that a process has to deal with, that has to process, for lack of a better word. You've got value demand. This is the first time demand created by the customer. And this is basically the request for whatever the process is outputting. The customer says, hey, I want a blue car. So all of a sudden the demand at the front of the process says, okay, start making a blue car. This is the demand that is directly related to making money, for lack of a better word. So now we have failure demand. Failure demand is caused by not doing something or not doing something right. And this can appear either in the front of the process or at the end of the process. Let me explain this. Let's say a person says, I want a blue car, and the process outputs a red car. We got this red car here. We go, okay, well, this is wrong. So we need to rework it. So you may put this red car back at the front of the process to reprocess it to make it a red car. So that's when the failure demand appears in the front of the process, it is re-entered into the process to correct what we did not do, okay, or that we did incorrectly. So, and when it appears at the end of the process, that was when we got the blue car and we wanted red. So failure demand can appear both at the front and the back. So failure demand, the queue coming out of an output can include failure demand. And if you put the stuff back into the process, the queue going into the process can also include failure demand as well, if we decide to put it back in there to rework it. Now, rework demand. This is demand that is internal to the process, that is caused by errors corrected internally without the external customer knowing. Let's say that the person ordered a red car, and all of a sudden the guy who's in charge of quality or inspection or in charge of the red spray gun goes, wow, this car's blue, we need to make it red. So he reworks it in the process. This is internally generated demand. So if you remember, we had the in-process, let me see, let's go back here. We had the in-service customers. Well, the in-service customers can include people, can include failure demand, which basically is products being sent back into the queue to be reworked. That was external. And you may have internal demand, rework demand that's internal, that basically causes the queue to stop, so we have to correct it internally. So the main difference between rework demand and failure demand is that rework demand is caught internal to the process. You're reworking it before it's spit out the process. Failure demand is caught by the customer. Okay, which usually, you don't want either one, but failure demand usually costs more, obviously. So usually. Okay, so if we look at the process here, this is the front end. So the failure demand can be refed into the front end to get reworked. It's something that's caught by the customer. Then the value demand is the initial demand for a product. So so it goes inside here, and this is the process. This is what's being done. All the work is being done in here. Everything's bubbling inside here. And if something occurs that doesn't meet specification or doesn't meet what the value demand is requesting, rework demand occurs to make it meet the value demand requirements. And then it's output. And hopefully, if it's output correctly, it goes off and gets sold, and we make money, and we never see it again. But if it comes out and it's incorrectly made, if we didn't do something, like we didn't put the fuzzy dice in the car like we said, or if we didn't do something right, we made it blue and not red, we may have to put it right back into the system here. Or in many cases, in some service industries, we may have a completely separate process where it may go into a new process as a failure demand for a second process. Okay, like a repair line for a truck lines or something like that. Any repair facility may have this. Okay, so this is important to understand how the demand can occur within a process. So ideally, we want to reduce rework demand. We also want to reduce failure demand, especially in a service operations. And this is the SIPOC. This is the supplier input process output customer. I just added this because some people are familiar with the SIPOC, especially if you are in project management or in some other types of operations management. This just shows where the this is 3 types of variation. We have we include arrival variation, which includes value demand and failure demand, like I mentioned earlier. So we include the arrival variation, which is the variation in the arrival of products entering the process. The process variation, which includes rework demand, and output variation. So when we look at improving the process, we need to keep these in mind, because if we want to improve the output, we may want to make it so that we have less failure demand. If this process is taking way too long, you can either improve the utilization, how efficient the process is at doing its thing, or you may improve how the process works itself by reducing rework inside the process. Or you can increase capacity if you're going to improve the utilization. I'm going to cover that in Kingman's equation in a minute. And then if we have a big stack here, you may want to do things like, for instance, there's a thing called demand smoothing, where we can spread the demand out. A very good example of this, let's say, it's very common for companies to order large lots of items. What you can do, if you have a very stressed process, you may say, hey, look, Instead of giving you one giant shipment all at once, let me give you several smaller shipments so I can spread the arrival demand over a longer period of time, the value demand over a longer period of time, so we don't have as much stockpile building up here, so much demand. Or if you find out that you have a lot of failure demand, you have a lot of product coming back in, coming from the customer, you may say, okay, fine, you know what, instead of clogging up this system, we may make a secondary system that we will just send the failure demand so that we don't clog up our main system. These are decisions that you can make, and Kingman's equation is very good at helping you understand how the system works. So onwards to Kingman's equation. Here's some math for you. It's not that difficult. So we've got three basic parts of Kingman's equation. Kingman's equation gives us average queue time. So here we have the variation within the system. Okay, C sub A is arrival variation, and C sub P is process variation. Okay, so we have utilization, which basically is load over capacity. I'm going to cover utilization separately in a minute. So we basically take rho with its small Greek character rho divided by rho minus 1. And then we multiply that by the time, the process time. This represents the end process time. So here we have the arrival variation, we have the process variation, and then the process time represents the time for the process to do its thing. So utilization is very important because it's basically load divided by capacity. And if we look at the previous example, it would be the arrival rate divided by the service rate for service processes, or the demand, value demand, divided by the time available for work. Okay, so I have it here that takt time can be used as time available for work or service rate wherever used. This is not correct, so please ignore this. This is not true. Matter of fact, let me just go ahead and I'm just going to draw a quick line through here. So this is not true. So please don't take that snuck in, unfortunately. So time available for work can be reduced by wasteful activity. Like for instance, time available for work can be reduced by rework demand or failure demand. Okay, so now when we deal with utilization, don't forget it's load divided by capacity. So if we can decrease the load, we have better utilization. Okay, a high utilization rate is not good. Okay, you want a low utilization rate, but unfortunately, a low utilization rate basically also means that you're spending a lot of money on unused capacity. So you want to look at there's a happy medium there. Okay, too low of a utilization, you waste money because you have capacity going to waste. Too high of a utilization, you run the risk of process failure. And if your load includes failure demand, rework demand, or waste, then a good way to reduce your utilization to make your utilization factor smaller is by focusing on those parts inside the process that increases the load on the process. So if you remember earlier, failure demand, rework demand, and waste. Okay, so your load is reduced by reducing the failure demand and the rework demand. Okay, we saw that earlier in the diagram. Let me go up to the diagram real quick. Okay, I'll have to clear all the drawing. Whoopsie daisy. Okay. So let's go back up to this drawing. So the load is inside here. So if we reduce the rework demand, and if we reduce the demand coming into the process, we can reduce, ideally, we want as much value demand going into the process as possible. This is a key and important thing to understand. We want as much value demand in the process as possible, because failure demand and rework demand works against our available capacity. Okay, so then you have your failure demand. If you have failure demand coming through here, this has to be worked somewhere. So you either clog up this process again, or you clog up another process. So directly, a good way to reduce your utilization is to attack your failure demand and your rework demand. You want as much value demand as possible going through your process. Okay, so going back to here. So reducing the rework demand and reducing the amount of work spent, work in progress, obviously. And reducing the waste reduces the load. So, because waste causes rework and reduces capacity. So that's, as we just showed. So it reduces available capacity. Okay, if you have a machine that spits out 1 million widgets a day, and your waste ends up using up 300,000 of it, you've lost 30% of your capacity to waste. So to increase your capacity, your available capacity, you basically reduce the amount of workload that goes into the capacity. Okay. So now, here's the utilization factor that's in that diagram. And as you notice, it's very slow curve here and a very high curve. This is because we go rho divided by rho minus 1. So this is rho divided by rho minus 1. And utilization, as you notice here, when we're at 0%, basically load is 0. So there's no customers or orders coming in. Okay, so if you have utilization at 0, or obviously 0. So if your utilization, let me turn on my annotation again. If your utilization is a very small number divided by your capacity, then it's going to start to slowly creep down this Q, this here, until there's a certain point when we get to about 80% capacity, when it really starts to shoot up. And as we get closer and closer to 100% utilization, basically your system's clogged up. Once you get above 100%, I guess in theory it's possible, but if you do your load over your capacity, your queue time basically starts to increase because you're not able to push enough product through the process to get the product out before it basically starts a backlog. So if your utilization is above 100%, you have an increasing queue. So it'll continually increase till infinity until you bring your load to less than capacity. So variability in your system shifts this curve upwards. So the average queue time. So if you have, let's say that you have variability of 3 hours in your queue, this queue would start at 3 instead of 0. Okay, 3, 4, 5, 6, 7, 8, 9, 10. But once again, the closer down this queue, this line you go, the closer to infinity your curve becomes. So although variability is a bad thing in your queues, utilization is a big thing. So sometimes you may want to say, well, what should I attack? If we go back to Kingman's equation, we have variation, okay, which is the arrival variation coefficient, and we use coefficients because it's a ratio of the variation to the time. Okay, so if we have a coefficient of 2 minutes over an hour, it's a very small coefficient. Where if it's 2 minutes over 3 minutes, very large coefficient, so it's much more important. So we use coefficients for this. Process variation coefficient. So do we attack this part here? Do we attack utilization, or do we attack the time? So in many cases they attack the time, and that's a good idea, but sometimes you can get better lift by pushing some of these. So if you can improve the variation, you could use like a control chart to understand the coefficient, how much variation is within the process. Sometimes reducing the variation can be very helpful. Increasing capacity always helps, but sometimes that's expensive. Maybe that's not something that you could do. And let's say if your utilization factor is down here, increasing your capacity might not give you that much lift. Of course, if your utilization is like 80% or 70%, yeah, bringing it down this way is going to drop it considerably. But if you're sitting down here, increasing capacity won't give you much lift or much improvement in your values. So sometimes you may want to look at your variation or your time. Okay. So you can calculate this using the control chart, or you can, or just a simple standard deviation of your process. You can use your time for the process, okay? And then you can calculate utilization, and then all of it put together gives you an average queue time, okay? So that was a quick crash course on Q theory, a quick crash course on statistical process control. There's an entire class that can be given on statistical process control. I'm not sure if SNU has that, but it can be an entire class. I've got loads of books on statistical process control, and I know of people who teach this, and it's very in-depth. One person I know gives a 6-month course on this in a factory where you learn it in a real-life example. So statistical process control can be very lengthy. So with that in mind, I will look forward to whatever questions you may have in class. Please let me know if I can help you out. This week, week 9, you have to turn in your final project. If you can have it due by the end of week 9, that'd be very helpful. If you can't, let me know. Unfortunately, because the amount of grading that's done in the last 2 weeks, I may not be able to extend it too far, but I would gladly work with you if you have any problems. So thank you very much, and I look forward to seeing you in class. Bye-bye.